Find the value of x, which maximizes the function z of x, using a genetic algorithm. In this problem, the quadratic equation negative x squared plus 170 times x minus 3625 is plotted from values of x equals 0 to x equals 200 for the positive values of z. The quickest way to solve this problem would be to compute x as negative b divided by 2 times a, where a is the coefficient of the quadratic term, negative 1, and b is the coefficient of the linear term, 170. However, we'll solve this problem using a genetic algorithm. Genetic algorithms work well for a wide range of problems. However, specific algorithms such as dynamic programming or quadratic programming perform better than genetic algorithms for specific types of problems. Normal search algorithms start with an initial solution and progress through multiple iterations until optimality is attained. Genetic algorithms start with a population of initial solutions and progress through multiple generations until the objective is satisfied. Since genetic algorithms cannot guarantee optimality, the term algorithm is a misnomer. Genetic algorithms should be considered a heuristic method because it is a process that has been developed through intuition, experience, and judgment. To begin, a population of feasible species are initialized and then tested against a termination criterion such as maximum fitness of a species, average fitness of an entire population, or number of generations. If the termination criterion is not satisfied, a new generation is produced by crossover, mutation, and reproduction until the termination criterion is met. For our problem, we'll use 5 generations as a stopping criterion, which means we'll start with the first population, then create 4 subsequent generations, and finally use the 5th generation to determine the solution. In this problem, we'll use a generation size of 64 species using a non-elitist model and initialize those species with values between 0 and 255, which clearly encompasses the optimal value of x. Next, we'll begin synthesizing our second generation of species by crossing over, or cross-pollinating genetic information between mating pairs. Of the 64 species in our first generation, the values of x for the first 8 species are shown here. Next, we'll represent these values of x as the sum product of binary numbers and powers of 2. Therefore, the first species of 153 would equal 1 plus 0 plus 0 plus 8 plus 16 plus 0 plus 0 plus 128. These values would be easier to read if they were in a table. The binary numbers for the remaining species are determined as well. If adjacent species are paired to interbreed, and we focus in on species 1 and 2, then crossing over means at a certain location in the data chain, the chromosomes are switched for the remaining length of the chain. During crossover, genetic material has been transferred, which has caused the value of x to change as well. It's also possible for there to be multiple crossovers between the two species, as shown here, between species 1 and 2. Other pairs may experience no crossover, as is the case for species 3 and 4. For this problem, we'll use a 15% chance of crossover between adjacent chromosomes, determined separately for each of the 32 mating pairs. The next step is mutation. The purpose of mutation is to introduce new material into a child species that was not present following crossover. Returning to our first 8 species, we'll choose to use a 2% mutation rate, which means there is a 2% chance that any single chromosome will change from a 0 to a 1 or from a 1 to a 0. Of the 64 values shown here, only one chromosome, in species 3, was mutated from a 0 to a 1. This caused the value of X3 to increase from 82 to 114. The mutation percentage should be kept low. Crossover should be the primary mechanism used to swap genetic material. The next step is reproduction. In reproduction, a fitness value is calculated for each species, and a new generation is synthesized based on the fitness level of each species in the previous generation. For example, species 23 currently has a value X of 55. This computes to a Z value of 2700. Since we want to maximize our value of Z, we'll define the fitness of a species equals Z if Z is non-negative, and that the fitness equals 0 if Z is negative. This makes the fitness of the 23rd species equal to 2700. As another example, species 47 has an X value equal to 161. The corresponding Z value equals negative 2176. Since the value of Z is negative, the fitness equals 0. After crossover and mutation, the Z values for the first 8 species are calculated, as well as the fitness values. Next, the fitness values are normalized such that the sum of the normalized fitness values equals 1. In reproduction, a new generation of species are created based on the normalized fitness of the preceding generation. Like natural selection, the more fit the species, the more likely it will survive. A second generation of species is generated. The binary numbers are filled in, and crossover occurs, with a 15% chance of occurrence, followed by mutations, which have a 2% chance of occurrence. In reproduction, Z values are calculated, as well as the fitness and normalized fitness values. Next, 64 new species are chosen for the third generation. This process continues for 2 more generations until the algorithm stops. If we create a histogram of the X variables for the first generation, we notice the data is scattered over the entire domain of X. In the second generation, most species have an X value between 50 and 100, and no species have an X value greater than 150. In the third generation, it becomes quite clear the optimal solution is between 50 and 100. For this third generation, we'll further discretize the 50 to 100 range using a delta X of 10. For this third generation, it appears the majority of species favor the x equals 80 to 90 range. Keeping with the same scale, the fourth generation also suggests the most fit solution is between 80 and 90, as well as in the fifth and final generation. When reviewing the possible solutions, the answer is B.